go ahead and get started while everybody's finishing up getting their food and everything. Welcome. Thanks everyone for showing up. It's a very good turnout. So we've had some really good turnout these last. This is our third meeting since we started the year up. Free. There you go. Exactly. Free lunch, PDHs. Can you ask for anything more, right? So appreciate everyone turning out. So before we kick this thing off, just want to talk a little bit about what we've done with the section and what we're moving into 2018. So again, we've had this is our third meeting for the year. So we started our first meeting up with a talk on ISA 101 standard. Then last month, Chan was in town and did a presentation on a hybrid safety and control transmitter function. And then today we're talking about wireless HART gas detection. A couple things that are going on with the section. The fall leaders meeting was just held this past week. Bill Brock, our secretary, went to that meeting. And so what we're looking at doing is probably doing a recap of things that are going on with the section corporately and internationally. We'll maybe do a recap in our next meeting in December, and then also talk about what we're doing here locally for 2018. So right now we're currently filling up the docket with technical presentations for 2018. There's several in this room that have expressed interest in doing presentations. So please get with me and let's nail down those dates. So we have open dates on the calendar, and we'll get people in slotted to do presentations. Also, this week that's going on in Houston, we have the Process Control and Safety Symposium is actually going on as we speak. In fact, Chan's company, United Electric Controls, is exhibiting at that show. It was yesterday, today, and tomorrow. So Chan was very gracious enough to fly over from Houston to be with us today and do this presentation. Also want to thank all of our sponsors. So pull that up here real quick. So these are our current sponsors. So we did do a sponsorship drive just recently. We're always open for sponsors. If anybody else wants to join in, all you have to do is just go to our website, hit the sponsor link. If you want to be a sponsor, it'll take you to a page. It's $150. You get your logo on our website. We show your logos at our meetings, and then you get the ability to sponsor a meeting as well. So you get kind of first dibs on their calendar if you want to sponsor a topic and present to the group. Thanks to everyone that's sponsored. Got a few new names on there. Bill's wife Barbara sponsored. She does real estate, and I think that's great that she's willing to sponsor us. We've got a Champion re-upped. Thank you. And they're in the room today and have expressed interest in doing a topic in the future. And so again, appreciate all of our returning sponsors and our new sponsors. Okay, and with that, we haven't we typically used to go around the room and introduce ourselves. So we'll do that again since we have a good group here. I'll send Bill around with a microphone and we'll just introduce ourselves for the benefit of the people that are outside. But just your name, company, and if you're on the local board, just let us know that you're on the board and in your position. So again, I'm Dean Bickerton, work for the Reynolds Company, and I'm the president of the section.
Bill Brock, the secretary of the section, automation specialist with Reynolds.
Wayne Welk, automation specialist with the Reynolds Company. I do marketing and the website for the section.
Chris Leonik, Patriotic.
Beth Walker, Monsanto.
Bob Philpott, CPU.
David Weiss, CPU.
Mike Mel with Jacobs Engineering.
David Reederer, Jacobs Engineering.
Arthur Zadaran, ArtZat Consulting.
Greg DeLon, Skurlock Electric.
Simon Nguyen, Phoenix Contact. Toby Miller, retired.
Gary Williams, MyTech.
Rick Matei, Moody Price. Brad Jordan, Champion Technology Services.
Ashley Dufresne, Champion Technology Services.
Greg Saunier, Champion Technology Services.
Larry Iverson, retired section publications chairman and what's the other? Historian.
Steve May with CPU.
Roger Reedy, Monsanto, retired. I'm the treasurer.
Eric Keller, EDG. I'm the vice president of the chapter.
So Jan, you all mic'd up?
I think so.
Turned
Test
on?
1, 2, 3.
All right. So I'll turn it over to Jan Reese. Again, appreciate him coming in from Houston from the Process and Safety Symposium to do our topic on wireless gas detection.
Well, thank you, Dean, and I appreciate the opportunity to get before the group again. What I'm going to present today is not content that I personally developed, but it was our Vice President of Engineering and Development that collaborated on the material that I'm going to show you, and it was based on a white paper that we've published, co-authored by Will Chin, who's our Vice President of Marketing and Development, our Senior Product Manager at United Electric, and a fellow named Greg Laframboise, who is worked for Chevron for years as the lead wireless technology expert, now retired. And so this is downloadable, and I can tell you how to do that afterward. I'm not a subject matter expert on gas detection, so the purpose of our team is to go out and share this information because it's all fairly new stuff. So this will be a sort of tutorial in some respects on wireless gas detection from 5,000 feet. The actual design considerations, I can point you to some recommended documentation on that subject, which ISA has published just recently in April for the application of wireless devices in non-safety instrumented system, IPL as they call it, independent protection layers, and also work that SINTEF in the North Sea has done on the subject of wireless in safety critical applications. Please, if you have questions along the way, don't hesitate to stop, and so we'll get into this right now. So we'll look at wireless detection as some background. We'll explore some of these pervasive customer problems that we've uncovered with our research. We'll present some solutions. We'll touch on some best practices in this evolving space called wireless gas detection. So we'll get right into it. So personal wireless gas detectors, often the pocket-sized ones that operators wear. This is an example of it. They detect several gases. It's probably the most ubiquitous kind of wireless gas detection there is right now. And it's certainly part of this architecture, if you will, at a plant to protect personnel. Some examples of fixed gas detection, which is what we're going to focus on, are shown here. So single point fixed monitors are usually installed in permanent or semi-permanent locations. And like the existing pressure and temperature transmitters, they have a single purpose to measure a process variable, very local to where they're mounted. Here's an example of an open path detector, which is designed, unlike the fixed point, to cover a wider area. But by that nature, it's not as effective at point gas detection. And of course, the gas concentrations that it's detecting can be affected greatly by the environment, including weather conditions. Ultrasonic gas detectors are designed, to listen for gas leaks, usually mass kinds of events where there's a noise generated by the leak. And these detectors are really looking at the volume of that gas, not trying to get down to the measuring the gas concentration. And these tend to be fairly expensive devices. And certainly more expensive than fixed gas detection. All right, we'll get back to now the point detectors. So these are placed in areas where gas emissions are most likely to occur. There may be areas where there is wired gas detection present already. The gas has to come in contact with the sensor itself. So these are vertically oriented always. And that's an example of a point gas detector. And further, an example of a wireless one that's now come on the market. So in terms of the market share, right, 65% are in this portable category, and about 35% make up the rest of those examples that we talked about. And breaking down the fixed gas detection market share, it's dominated by the fixed point gas detectors in this class, 12% in this ultrasonic area, and 3% of the open path type. And as it is now, only fixed point gas detection is available in this wireless type of configuration. The others, well, they're all power-hungry devices, but certainly the fixed point gas detector is less power-hungry, shall we say, than the other examples that I gave. And such, it lends itself to a wireless solution, battery operated. I'm sorry, I'm stepping in front of you. So here's a question: why wireless, right? Wireless plays a large role in providing that freedom to locate a detector in oftentimes a hard-to-reach place or an inaccessible location. Of course, the placement varies by the type of gas. It also varies by the application, which is to say, is it an area where there's a high risk to personnel, or is it more likely to be an area where there's a more a larger risk of explosion? What are we dealing with? We're dealing with methane, for example, CH4, that's lighter than air and tends to collect at higher locations, right? So you can imagine the ceiling of a garage where a CNG vehicle may be operating, just as a real-life example. Enclosed spaces become high-risk locations where there may be methane present. And the other biggie is H2S, right? Hydrogen sulfide is heavier, in contrast, than air, and will collect down in lower areas. And this is dangerous, right? Because it lurks around, it can move around depending on the weather conditions and the air flow. Wells and vaults are one of the areas where H2S collects. So detecting gas from inside those enclosed areas is essential so that an operator, a maintenance person doesn't walk into the space unaware, and because it can be fatal very quickly. analyzer housings would be one example of that, and we'll get back to that in a little bit. So the issue that has plagued wireless gas detection, right, is this lack of power and wiring. These field devices have to transmit their measured value to a host system, a monitoring station, and it's accomplished easier with pressure, level, temperature, because the sensors tend to be a little more forgiving in terms of battery or power consumption. And so the big trip point for wireless gas detection has been how do you power it in a way that makes it practical to deploy for periods of time, because you don't want maintenance folks having to change batteries, right, every 3 months. That's a big cost. It's a big total cost that goes beyond just the cost of the battery. So we did a lot of research in this area, drawing on outfits like the Fieldcom Group and this outfit called Burge Insight. ARC was another company that supplied us data. What they say is that these wireless HART, that wireless HART is one of 5 of these global standards. And I've got a list of the others, Zigbee being one, ISA 100 being another. There's a standard that's emerged out of China, that driven by academic and process automation interests there, that had a real compelling need. But wireless HART is certainly the most ubiquitous of these open protocols. There's about 26,000 WiHART networks, we estimate, operating in over 140 countries. A lot of networks. A lot of interest from vendors and manufacturers like my company that are trying to develop products, and certainly there have been many wireless products using the WiHART standard developed to date. About 50 we guess in total classes of product in this WiHART enabled area, and about 40 million devices worldwide installed. It's estimated that wireless sensors will grow. The ones dedicated to this industrial Internet of Things by almost 30% annually, and that they're projected to reach 62 million connections by 2021. There's another way of looking where this is growing dramatically. This is just the fixed point wireless gas detection metrics, if you will, or forecast. Now we had to wrestle with which one of those open standards to embrace as a vendor. We looked at mostly ISA 100 and wireless HART. They're the most common of these open IEC sanctioned standards. We selected wireless HART for the reasons that I just showed you in the previous slide. There's far more acceptability right now for wireless HART than there is the other standards. And the majors that we meet with have really delineated 2 paths, wireless HART or ISA 100. And they're different, and they have different attributes. But the piloting and the testing right now at majors is really focused around one of those 2 standards. at least in the oil and gas space. I can't speak really for chemical. I'm a little reluctant to throw out figures like this without citation. I went back and asked about that. My boss said that the subject matter experts that we surveyed that come out of vendor companies, right, and others that are in the consulting and engineering realm have said that the wireless HART standard is moving toward this 99% reliability. Reason being, the management of the network and the development of the devices in terms of what they can communicate and the understanding of that underlying architecture, right, and the design considerations that go into the design placement of devices and the deployment, this is an achievable network reliability standard for wireless HART. This is an example of what wireless HART does. It forms this mesh. So it begins with a gateway, the installation of a gateway, and the deployment of devices that have multiple paths back to the gateway. If any of you had experience with wireless HART, you know about this mesh architecture and how it differs from, say, the star topology that you see with ISA 100. Both have their strong suits. We have gone this direction because of this self-building and self-healing attribute. We know a lot of our customers are in plants where there's a lot of piping, there's a lot of skids, there's a lot of congestion, right? There's a lot of need for figuring out, if you're going to deploy wireless, how you work the roadmaps back to the gateway to achieve high network reliability, right? And with wireless HART, this central feature of redundant pathways is important. So if an obstruction drives into the path, could be a truck, could be something else, and blocks that path, it has another way back to the gateway. So these devices, though they may be for gas, they may be for pressure, they may be for temperature, they become nodes in that network or relay points. So when this obstruction takes place here, right, this could be a pressure transmitter, and it may determine that the best path back to the gateway is this way. And it's not activating the measurement part of the device. That's sort of on all the time and has a fixed level of power consumption. What it is doing is turning on the radio transceiver to basically pass the published information from the device on through this redundant path back to the gateway. This simplifies, of course, its commissioning. It's because you get these multiple options that are created. And it's natural that the more devices you add, up to a certain point, the stronger that mesh network becomes. The cofactor that gets involved with the expansion of the devices has to do with capacity in the gateway to process the information. So there's a lot of considerations that go beyond just the number of devices. But the basic principle is when you expand the number of devices in the mesh, the network gets stronger because it has more options, right, for getting back and publishing its information. Other attributes, As I mentioned, the interoperability with other wireless HART devices, the use of a field communicator is the only piece of accessory hardware you need to assist this device to join up with the network using two parameters, the network key and the network ID. We've commissioned these devices in some locations, and it's quite remarkable how simple it is if the design considerations have been respected from the beginning. The wireless HART standard has a way of optimizing those signals too. So the path that's the redundant path from one device to another gets optimized such that if there's less than optimum conditions in one path, it will pick another path and even channel hop if there's noise. This comes from Pepperl and Fuchs. It shows a wireless HART topology, if you will, and shows this interoperability. So it's not just type of device, it's also manufacturers that get mixed into this mesh. And as long as they're adopting the wireless HART standard, this interoperability is a feature of wireless HART. So a couple of footnotes, right? In heavily obstructed areas, signal distance can be affected. The point-to-point line of sight feature is about 800 feet. I mentioned the frequency hopping, a way of optimizing that path in the event of interference on one channel. It could be noise. And security is built in. Let's step back again and look at the marketplace. So what's changed in the marketplace? There's, of course, this compelling need to reduce complexity while increasing reliability. There's an interest in open protocols and getting vendors involved to design and develop smarter devices. They can do more things, but hopefully not too many things to confuse. And at least where the industry is now, wireless HART gas detectors are intended to coexist with the wired devices that are in place. So I heard the other day from a major, for example, that they've changed their design practice, their engineering standards to eschew or prevent wireless solutions in safety critical alarms. And the example they gave was a pull station for an eye wash station. So this major said, you know, we've determined that after some consideration to be a safety critical alarm, and our decision now is not to permit a wireless device to be used in a safety critical alarm. So this coexistence is meant as a deployment where it would serve a monitoring function. It would serve to augment what's already there. It would serve to provide a comparative value for what's being detected. Now, not all examples involve those decisions on safety critical, right? So you can deploy a wireless HART gas detector in many places where you have uncovered locations now, and gain a great benefit, of course, from that for that monitoring where there may not be any monitoring existing now. So I touched on a few of these places. It's a cost-effective way for deploying protection, additional monitoring in difficult-to-reach places. It complements these existing wireless HART and wired HART devices in what would be an existing wireless network, and in brownfield facilities especially. Abandoned wells, for example. It provides an instant monitoring solution. Those uncovered areas are significant, right? There's a lot of places that are uncovered now. And until these wireless solutions came along, the ones that operators felt comfortable in adopting, there weren't many choices, you know. I was in Midland last week for a couple of days, and hydrogen sulfide, of course, is a big problem on those abandoned wells and in oil production fields in general. And tank batteries, for example, with these thief hatches, you know, and a lot of unprotected space right now. And one operator said, you know, this is a can of worms and we're not sure we want to open it, but this at least gives us an opportunity to consider places that we heretofore have not considered because the cost was too prohibitive. And no power, no infrastructure. Now, battery life has really been one of the trip points, right, for wireless HART gas detection. And we've changed that game, or vendors have changed that game, by breaking through this barrier of short battery life. And I can't go into the details of how vendors do it. I know how we did it. It's proprietary technology that actually some of our earlier products have taken care of as well. The idea of being able to use so little power to get functionality out of a device like a pressure transmitter or a temperature transmitter. And so in summary, we've come from proprietary to open systems. We've come from a situation where there was a fairly costly initial investment in wireless infrastructure to being able to take advantage of existing wireless infrastructure. Come from limited battery life to 5-year battery life that's warranted. Devices with limited diagnostics to expanded diagnostics, a long deployment period to shorter deployment, to a steep learning curve to a more forgiving understanding of all of this and using the available expertise to take advantage of these solutions. And finally, from a system that was somewhat difficult to maintain to an easier way of maintaining it, simply because we've advanced in terms of what we understand. The operators have advanced in terms of what they understand about, you know, design considerations and in wireless networks, pinch points and battery life and things like that. Let's just review the gas detection hazards we're talking about. Three main types: toxic, combustible, and asphyxiate. The toxics are measured in parts per million or parts per billion. Examples would be hydrogen sulfide, CO, and chlorine. Combustibles would be methane, propane, and the derivatives. And then asphyxiates can be either and others. So we looked at which gases to roll out sensors for first, and our research said hydrogen sulfide, because it accounts for so many fatalities. It's fatal in, this has high concentrations. It can be fairly low concentrations. I mean, the alarms for majors that majors set oftentimes for hydrogen sulfide are down in the 10 ppm area. It's a big risk in upstream oil and gas because H2S is soluble in oil. And it's colorless. It smells like rotten eggs in low concentrations, and then by the time those concentrations increase to the point where they become fatal quite quickly, your sensing abilities diminish significantly. The olfactory mechanisms in the human get compromised very quickly at higher levels of H2S. So, and by the time that happens, it's too late. Methane, you know, there are examples on the internet of methane cloud explosions. They're all over YouTube. All you need, you know, is an ignition source and oxygen. And when we researched which gases really to attack first, it was these two, hydrogen sulfide and methane, making up a large percentage of the problem. Again, this is sort of centric maybe to the oil and gas space, and there are other of course risks that exist in chemical and chemical mostly. Some of the pervasive problems, you know, the costliness of installing wired detectors, the fact that infrastructure is sort of maxed out in many locations, can't be expanded. It can take months, right, to trench and to lay conduit and to install panels and all those things associated with wired hardware. The proprietary wireless has been sort of pushed to the side somewhat by these open standards, at least among major operators. They don't want to deal with proprietary systems. The meeting I had, for example, last week, that was the first thing they said, is that we don't want to deal with, we won't look at any proprietary protocols in terms of wireless. The unavailability of line power. Other customer problems that we've uncovered, personal detectors sometimes aren't accurate. They alarm locally, but not remotely, oftentimes. And in those situations, by the time you can get help to the guy that's fallen down, it's too late. They're worn by individuals, of course, so the detection happens where the human is present. And that, of course, is not everywhere all the time. So a lot of the infrastructure can't be covered with a personnel detector. And then, of course, the question, I had someone say to me, yes, and the other systematic stress that we have with personnel detectors is, did they charge the battery, you know? When's the last time it was calibrated, you know? All of those things that operators large and small worry about, you know, in terms of the implementation of that kind of protection. Any questions before we keep pressing on here? I'm more than halfway through. Yep. I don't believe there are any wireless HART personal detectors. No, they're all proprietary systems. Does anyone else know the answer to that? I know that there are no wireless HART. Again, there may be limitations in terms of what goes in. Right. Yeah. I wouldn't disclaim that it's not possible, but I don't think the technology is there to take a personal. Because the wireless HART requires a whole bunch of other things, the security encryption. You know, so it takes more software than a personal detector. Personal detectors are designed for now, but it's a trend. It's, you know, I don't want to say that it's not possible with technology the way it advances. Who knows? Any other questions before we continue? So monitoring the unreachable, it becomes one of the strong reasons for looking at wireless, improving that coverage, avoiding the cost of additional wiring, right? Doing it where and when you need it, so temporary work locations. We hear a lot about that with some of our customers now. Some of the places of where and why: storage tanks, piping, rotating equipment, perimeter fences, wellhead, enclosed spaces, vaults. The reasons that we mentioned: avoiding the cost of pulling wire, line power, or designing and installing additional wiring, conduit, cabinets, etc. And this time constraint is a big one, right? So not enough really time available in the day to contemplate a lot of additional wired gas detection. Chevron really informed the design of this product here. It was for fence line monitoring, and, you know, in the predictive maintenance area. So our collaboration early on, which is related in that white paper, had to do with a concern in a fairly remote location across a highway from the production facility. So storage and fence line for, they wanted to reduce the number of inspection rounds. They wanted to cover pipes, valves, tanks, compressors, things like that. So they were looking really for expanding the monitoring in an effort to increase productivity. Here's an example of one of the earlier deployments, a remote drill site where there's little wired infrastructure and no possibility for adding power, no desire to add power, and get into the trenching and the in this case there was distance between the controller and the piping. There was an existing HART network and a SCADA system that allowed this interface. This is the essential architecture: gas detector, the ROC 800 gateway, the central control. So this, in this case, became the gateway for the network. Here's another application: analyzer housings. These temporary confined spaces where there's analyzing going on, sampling going on, and there may be available power and a HART gateway, but some distance from the control room. And you go inside the building, and you can see the one device up there, and then a closer look there. Here is a coke refinery that's using a wireless HART gas detector to detect H2S. This is what I'm talking about, of course, with the trenching that's required to expand this coverage. It's exceedingly costly. The temporary work area is a good application. And so that gets to the question of how do you design this so that it can be mounted quickly and in a temporary situation. And so vendors have developed these, quick mount brackets, these stands that can be moved around. So if you've got temporary work going on, it's not, there's a way of expanding coverage very quickly and optimizing that coverage by moving devices around. This was an early application with this Silicio Canyon blowout in Southern California. Massive, disaster. And now the California regulatory authorities are saying, well, we don't really care much what the EPA is doing. We're going to implement these regulatory standards for methane detection statewide. And so this is one of the early deployments of a wireless HART gas detector in this area. Another California company, the Southern company, called Central Valley Gas, has these Christmas trees, where they are installing wireless HART gas detectors in this sort of surround 4-point configuration and monitoring levels so that they can optimize the location of the gas detection. They may remain with 4, or they may be able to cut it down to 2, perhaps. But they can. This is ongoing right now. They brought in a company that has this infrared camera that can really get quite a resolved view of the plume, and that, of course, helps inform location placement. So this is a gas detector and Emerson gateway, and then this Modbus input to a laptop right there on site so they can monitor. This is the world's largest refinery in India. The fence line is 80 miles long. And you can imagine the challenge of trying to protect a facility like this. So we're over and talking to those folks. They've been an earlier adopter of some of our other products, not gas detection, and so I think we're going to see a lot of business out of this is Reliance. They are looking at it as a complement also to their fire and gas system. So you have a fire and gas architecture in place. You probably have wired gas detection supplying analog 4 to 20s into the fire and gas control system, talking to the host system. And now the question is, can you expand coverage and add some additional redundancy? This issue of diversity of technology, gets talked a lot about in SIL applications and safety instrumented systems. How do you reduce the risk of common cause? And of course, diversity is one of those areas that is promoted as one of those design considerations for reducing common cause. Is it done in practice? Sometimes, but not often. And this, in my view, presents a great opportunity for adding diversity to a system like a fire and gas system, where the only safety variable output, as we talked about a month ago, would be the analog input to the fire and gas system. But this can serve as that redundant check, that informative measured value, that comparison. So it seems diversity is going to come of age, I think, with this deployment of wireless technology, where they may rely on the wired system as the primary safety variable output, but have other devices that can serve as redundant checks and maybe inform decision making before a trip is executed. This is going to be important in the upstream oil and gas production. As these wells get more efficient, they don't want a spurious trip taking the well down, right? I heard that from an operator recently. So how do you do it? Well, this is one way you could do it, by adding some redundancy that's diverse. Architecture, sensor, gateway, Modbus or Ethernet, DCS, alarm control, fire, first responder. Okay, getting near the end. The best practices, so far as we have been able to discern, I might have put this out of order. But the idea of deploying gas detection with long battery life, true wireless devices, not these kludged together systems with battery and transmitter and separate node. You know, the idea of integrating, you know, gas detection into one footprint. That's sort of been our mindset. And identifying areas not protected, looking for ways, ensuring ways of testing and maintaining, looking for the expanded role of gas detection, and testing the systems ongoingly, right? FieldComm's got a lot of good information. This is the organization that is the arbiter of the wireless HART standard, also ISA 100. We're hearing from the majors that this is where they're going with deploying open wireless communication protocols, not proprietary. There's a lot of good reason why the mesh network is the way to go. Registered devices, right? Vendors have to get their devices certified and registered to the standards in order to be players, and testing these solutions with host systems and really optimizing that deployment, right? So that the network health is as important as just the measured value that the device can provide. These entities, ISA, has published some good guidance on the application of wireless in non-safety instrumented IPLs. So this is downloadable from the ISA website. The working group was under that Functional Safety Working Group 84, S84. In the future, that not too distant future, that will be ANSI ISA 61511. So the harmonizing of that ISA 84 standard is being balloted very shortly, and will be sort of integrated and called ISA 61511. But their guidance on non-SIS safety instrumented systems, I have this up here if you want to look at it. And then Syntef has published a good report called Wireless Instrumentation for Safety Critical Systems. Now, there's only one device that I know of, so the number of players in these wireless spaces is very limited now. I can count only 3, and one of those, a very major automation supplier, hasn't released their product yet. So United Electric has a product. Gas Secure, which is a Draeger company in the Netherlands, they have a wireless ISA 100 gas detector. It's pictured here. And then Emerson has announced the release of their 928. And it may be on display over in Houston right now. I'm not sure. Any questions? Yes, Arthur.
The 5-year battery life is intriguing. I'm a little bit of a skeptic in general. It's kind of what I do for a living. And if something gets up to 48 miles to the gallon, so what does it go down to?
Yeah.
So if it's up to a 5-year battery life, what does it go down to?
I'm glad you asked that question. These wireless HART devices, such as they are, have update rates that can be configured. In the gas detection world, this one that has the 5-year battery life has is based on the minimum update rate, 8 seconds, right? And one of the variables that the device publishes is the battery voltage, so that can be monitored, the way you would monitor the measured ppm or percent LEL. The device reports, publishes based on that 8-second update rate, temperature, and days since calibration. So in the case of this device that I'm referring to, 4 of these variables published every 8 seconds, and the battery life is warranted against that 8-second update rate.
Would that also be affected by its participation in the mesh?
Yes. Well, right, and so this question came up about the other day about these pinch points. You know, if you've deployed it, the mesh, and you're exercising one device more than another, and that the formula for calculating that battery life took into consideration those pinch points. So the manufacturer warranties it at 5 years.
Under optimal conditions.
Well, yes, the conditions that we defined, 8 seconds. It takes into account.
And what's the battery replacement cost?
$350 list US. The batteries are hot swappable, so they can be swapped in a hot area. The sensor is hot swappable. I think it's probably worth me holding this up to inform a couple of things. We showed Chevron up there because they had informed the design of this particular one, and they were concerned about attributes like an external wave bump testing, the battery life, which I spoke of. They were very concerned about that 5-year being a minimum threshold for battery life. And they didn't know at the time whether it was achievable or not, nor did the developers. They were concerned about operators, maintenance folks, and what's involved in deploying instruments. And you can imagine in a hard-to-reach location how difficult it could be to change a sensor, for example. And so they informed this by saying they wanted 8 pounds of pressure as the spec to pull this sensor off and swap it out. So it was down to that detail. They were concerned about this, the bracket, and how quickly it could be mounted, either a surface mount or a 2-inch pipe, vertical or horizontal. So they were concerned about things like that. They were concerned about this having only one way to go in. So this got keyed, so it could only go in one way. They were even concerned about the robustness of the antenna. They wanted the maintenance guy or gal to carry it around by the antenna and make sure it was robust enough. So that really informed a lot of the design of this one example. Yes, sir.
What kind of batteries?
These are lithium thionyl. There's two of them in there. And the battery isn't so much the proprietary device as is the software and the circuitry.
Can
Yes, sir.
the gas transmitter, can it be calibrated separate from the device itself? In other words, you have some calibrated, pop it in and just take the one and use it?
Yes.
So you can be calibrating it outside of...
Oh, excuse me, the remote calibration. The vendor that's developed this has got that on the roadmap. Yeah, because that was one of the things the operators asked for, some way of remotely calibrating it. Right. And more of this technology is being deployed, the smarts into the sensor itself to allow that. Yes, sir.
The open protocols that it uses, how robust are those as far as security? Is it encrypted data being passed back and forth? It's a separate protocol. jamming?
Well, this was one of the considerations, the big considerations for the FieldComm group in developing a standard, because security was top on the list, and I'm afraid I don't know enough about how that was accomplished, but the the development and the sanctioning of that standard by the IEC required getting through those hurdles about security for both HART and ISA 100. So encryption is part of it, is built in, and the FieldComm group, if you go to that website, has a white paper that addresses those issues of security, very high on the list of considerations for the standard.
Is the gateway keeping track of all the statistics on the hops and the paths that are being utilized?
Most manufacturers of the gateway, right, have software that runs that, network management software that's keeping track of that, the handshake between the device and the gateway. So the passing of the packets of information, the real-time stamping, so you can just discriminate between what's stale data and what's real-time. Yeah, so they've taken that into account in the network management elements of the gateway itself.
So if you were trying to identify a particular device that was actually getting overloaded because too many packets were going,
right,
it would be at that level that you would detect that?
Yes.
The connection between the mesh network, the advantage of it, multiple paths of connections, but then the connection between the gateway and the controller or PC seems like single point of path, single path.
Yes, and that's, I think, one of the barriers to using it in a safety system. The choices are, and this is an area that I'm not familiar enough with, but you know, there's basically the Ethernet path and the Modbus path. The development of this gas-secure device involved the co-development of something called ProfiSafe. And again, this is an area I'm not really strong on right now. But this is meant to address the criticality of that communication back to a host system. And of course, any pathway back to the host, if it's a single pathway, is vulnerable. And so the vendors that deal with these solutions are, dealing with that issue of how to make those communication paths redundant, fail-safe, less susceptible to common cause. And some of that has been delineated by the functional safety standards that require that kind of separation of that communication channel. Yes, sir.
Back on the battery issue again. You said lithium ion, right?
Thionyl, I think it's called lithium thionyl.
Oh, okay. Is that a rechargeable battery?
No.
Okay. So it's in 5 years. Does it have to be degraded at all because of the environment that it's in?
It's that 5-year threshold that the manufacturer has represented and warranted is based on that 8-second update rate and also the ambient temperature limits that at the moment are -20 at the low end, and I have to look at the high end. That temperature T ambient is going to be expanded to -40. So the data that is required to rate those temperature ambient temperatures will allow it to operate from -20 to to plus 50 C. Yeah, minus 4 degrees Fahrenheit to 122 Fahrenheit, or -20 C to 50 C. And as I say, the Intertech who did the certification of this particular device will soon be rating that at -40.
Is this on now?
That does not have a lithium thionyl battery in it. It's got a couple of AA batteries that's powering the display. But it is on, yes. And there's a methane sensor in there now.
Okay.
Well, I appreciate all your questions. Are there any more I can answer? Well, thanks again for inviting me back, Dean, and thank you for your time and attention.
Thanks everyone for attending. You can just leave your